So in this video, we're going to dive deeper into the response of underdamped parallel RLC circuits. And this will conclude our discussion of the parallel RLC circuit because we will have talked about the overdamped case and the critically damped case in the prior videos. So underdamping is going to occur when the actual damping factor alpha is less than the resonant frequency omega naught. And under this scenario, the solution to the characteristic equation is actually a pair of complex conjugate values. Now, if you think about in the first video that we recorded in this chapter, we talked about how complex conjugates through Euler's identity can be manipulated into actually forming sinusoidal functions. That's exactly what we're going to see here. These are going to be the first form of this RLC circuit that actually exhibits a little bit of oscillating behavior. Up until now, the overdamped and the critical damped case have kind of just converged down to zero and never actually went negative. They've never swung like a sinusoid. So what we're going to find is you actually don't need complex numbers if you go, unless you're working through the derivation of the solution to this circuit. However, the way that it works is if we allow our complex frequencies, if we write them in our standard form, as we've done so far, minus alpha plus or minus, sorry, I'm looking for my cursor there it is, alpha squared minus omega squared. All that we're going to do is factor out a factor of -1 under the argument of that square root function and utilize the fact that we can pull that square root of -1 actually out of the argument, which is just basically going to change the order of the difference inside the square root. And for those of you that may not be familiar, when you have the square root of -1, that is the definition of the imaginary unit. It's usually denoted by I, but it's going to be denoted by J in the case of all electrical and computer engineering courses because I is already so prevalent in describing currents within circuits. So really, this is just a little bit of manipulation to explicitly show that it is a complex number. Of course, this scenario could have become complex, but basically what we're doing is when we're considering the specific case where we know it will be complex, we're doing the manipulation in advance in order to get more interpretability. And what I mean by that is if you notice, we're going to define that term, the square root of omega naught squared minus alpha squared, to be the natural resonant frequency. You don't see that term used very often. However, if you go through, as is shown in the text, and you write that general solution, you can see that this has a very interesting form, right? If I go out of the actual kind of complex number form with the complex exponentials here, and I look at the final result, which can be derived through Euler's identity, I can clearly see the decaying exponential part of the solution, the e to the minus alpha t, multiplied by the oscillating portion of the solution. We still have these two unknown constants, and I'm going to change that real quick. That should not be 1, that should be B2. Sorry about that. You get to watch editing in real time. But the key point being that you have the oscillatory part and you have the damping part separate. And when you add two sinusoids of the same frequency, hopefully all of you are familiar with the fact that it's going to be just a single sinusoid. The relative values of B1 and B2 are just going to determine the phase shift. It will still have that frequency, omega d, corresponding to the natural resonant frequency. So I just wanted to show you before we worked an example of how underdamped circuits, their actual responses can vary substantially depending upon the actual value of the resistance, basically how underdamped they are. If you go through and you look at those actual formulas, one of the things that may be confusing to you is naturally, since you think about resistance as being the mechanism that takes energy out of the circuit or actually damps it, that as R increases, you would think it would actually become more and more damped. But if you look at those formulas, that's not actually the way it works. So as the R value increases, this thing will go from exhibiting what looks like overdamped behavior, where you have that initial upshoot, and then you're converging towards zero and never going negative, to actually swinging fairly dramatically in a negative fashion. So this just shows you how sensitive the response of this circuit is to the actual level of underdamping that you have. So just for a quick review, a visualization rather, not necessarily review, before we do an example problem here, if you look at the response of a circuit where you're just varying the R value in such a manner, so hold the L and the C value consistent as they do in your textbook derivation, and just allow R to change, that changing of R will drive the circuit through the three different scenarios of responses that we've discussed. When R is small, you'll see an overdamped response shooting up from an initial value of 0 for the quantity that we're talking about here, going to a maximum value and then exponentially decaying down to 0. In the case of critical damping, that is basically the largest you can make R such that this never actually crosses 0. It doesn't exhibit any kind of oscillation. And then in the underdamped case, depending upon how underdamped it is, you'll notice that this curve swings slightly below 0, but you don't see the oscillation much because the issue is that energy leaves the system before it can oscillate to actually wildly in this case. But if you were to keep increasing R, you would see more of that kind of wilder oscillation that you saw in the last case. It's still eventually going to zero because of this e to the minus alpha t term. It's just really a matter of how quickly it goes there and how much oscillation you see. So I wanted to show you another example problem. We're given this circuit and we're asked to show that the current exhibits this type of natural undamped response. If you notice, you have a decaying exponential multiplied by the sum of two sinusoidal functions, one a cosine, one a sine, but both at the same frequency. So let's go through that derivation. I'm going to go over to my .cam, and the first thing that we want to do, hopefully you're seeing the pattern of how these problems actually work. You need to draw circuits basically to determine the initial conditions. And the way that we do that is we derive the solution to the circuit typically immediately before either a switch is flipped or a source goes on and off. One thing I want to bring up, if you look at this source, it's 3 times u of minus t. Remember that this is the unit step function, but whenever we make the argument of a function negative, so the unit step function goes from 0 to 1 at t equals 0. When you make that argument negative, you're basically reflecting it about the y-axis, so it will go from 1 to 0. So this will actually turn off when t equals 0. However, before t equals 0 and at the point of t equals 0 minus, we still have the source there. In addition, if you look at the nature of, sorry, I shouldn't keep switching back and forth, this switch is closed at t equals 0. So before t equals 0, it's open. You can kind of just ignore this path. And what that means is that 48 ohm resistor won't be shorted out. It will be once the switch flips. So basically all we have is a DC 3 amp current source driving this capacitor. This branch has a resistor and an inductor in it, and this branch just has a resistor. But remember, if the circuit has been operating for a long time, if it's in steady state mode, to a DC source, the capacitor is just going to be an open circuit and the inductor is just going to be a short circuit. And that's exactly what I have on these solutions here. Just open up your capacitor, short out your inductor, and solve that circuit. And hopefully everyone recognizes that all you have going on here, and I've left a little bit of complexity in here just to show you where the capacitor went and where the inductor went. But if you totally took those out and you took out the markups, you'd see that basically all you have is a 3 amp source driving a parallel load consisting of a 48 ohm resistor in parallel with a 100 ohm resistor. So this is by definition a current divider circuit. If we seek to solve for the current through the actual inductive branch, that's generally the approach. We're looking for inductor currents and capacitor voltages, which in a parallel circuit are all the voltages. This inductor current at 0 minus is just going to be the portion of this current that's routing through the 48 ohm resistor. So take it and multiply by the division ratio. Remember that for current division, the quantity in the numerator is actually the quantity that you're not of the resistance of the branch that you're not solving for, because you want, as in this case, if we're finding the current through the 48 ohm resistor, as the resistance of this branch goes up, the current through the other branch will go up. So that's the current division ratio. So 3 amps times 100 divided by the sum of the two resistor values, 100 plus 48, that actually turns out to be 2.027. I wrote that wrong originally, and then you'll see it kind of carried out through the remainder of my calculations, unfortunately. And then in addition, once you've determined the current through the inductor, you note that since that VC is just measuring the voltage across all of the parallel branches in the circuit, that current through the inductor, which is acting like a short, is also the current through the 48 ohm resistor. So we can find the voltage across this branch by just taking IL and multiplying by 48, which is going to give us 97.3 volts. Now let's redraw the circuit right when the switch actually goes through and closes. So once this switch closes, it's going to short out the 48 ohm resistor. So we don't have to draw that in our updated circuit. In addition, at t equals 0, this current source is actually going to turn off. So what that's going to leave us with is just a capacitor. Once this resistor is shorted out, this branch will just be an inductor in parallel with a resistor. So it will be a source-free, where we're at RLC circuit once t is greater than 0. So that's all that I've redrawn here. If you notice again, the current source is removed, the 48 ohm resistor is shorted out, and we know that by continuity, the current through the inductor has to be the same as it was at t equals 0 minus. So that's IL of 0 plus is just IL of 0 minus, which is 2.027 amps. And in addition, the capacitor voltage also can't change instantaneously. So VC 0 plus will just be VC 0 minus, which we computed over here to be 97.3. So these are just continuity resulting from the IV relationships for the inductor and capacitor. In addition, in an RLC circuit, we can compute the kind of characteristic parameters that govern our solution namely the damping factor alpha is just 1 over 2 RC. If you plug those values in, you'll get 1.2 inverse seconds. In a similar fashion, omega naught, the resonant frequency is just 1 over the square root of LC, and crunch your numbers there, and you'll get 4.899 radians per second. You notice that omega naught is larger than alpha, which means that we have an underdamped response. So our complex frequencies will be complex conjugates of one another. And we know to use this general form of the response for any quantity in the circuit, including the current. Namely, what we have going on is we have exponential decay being multiplied by the sum of a cosine and sine function of the same frequency, but note that we have the two unknown constants that we'll solve for by our initial condition. What is the frequency of these cosine and sine functions? Well, that's just our omega d, our natural resonant frequency, which we can compute as the square root of the two parameters that we solve for up here, omega naught squared minus alpha squared. If you plug those in, hopefully you'll get 4.750 radians per second. So for the oscillation that exists in the response, this is determining how quickly it occurs. Now we're going to need, we have an initial condition on I of t, right? That is just the inductor current. However, in order to solve for both of these unknowns, we're going to need an additional initial condition on the derivative of that inductor current. So what I'm doing here is I'm just taking the derivative with respect to time of this general function. The way that you can view it is this is like f1 of t, and this is f2 of t, and you want to use, this is all the product rule. So what I'm going to do is I'm going to leave the first term alone, e to the minus at. I'll take the derivative of f2 of t. Remember that the derivative of cosine is negative sine, and this is also a chain rule function. You have to take that omega d term out. So the derivative of just this term is going to be minus omega d b1 sine of omega dt. And then by linearity, when I take the derivative of the portion that I'm adding on, the derivative of sine is cosine. Don't forget your chain rule, omega d b2 cos omega dt. And then by the actual product rule, I left f1 alone. I took the derivative of f2. Now I needed to take the derivative of f1. Since it's an exponential function, the derivative of e to the minus at is just going to be minus a, e to the minus at. And then if you notice, this term here is all of f2. Now this looks really intimidating, but remember the initial conditions are enforced at 0, and all of these functions have simple behavior when their arguments are 0. The exponential of 0 is 1, sine of 0 is 0, and cosine of 0 is 1. So how will we actually relate the quantities that we have, which are the initial voltage across the entire circuit or the capacitor, to this quantity that is the derivative of the function that we're solving for? Well, remember that di dt, what does that remind you of? Hopefully it reminds you now of the actual VI relationship for an inductor, V equals L di dt. So what that means is that this function is going to be proportional to, by 1 over L, the actual voltage in that circuit. So the value of this function at 0 plus is going to be proportional to the value of the voltage at 0 plus. 1 over 10, that 10 is just the actual inductor value in the circuit. And this 97.3 is just the value that we solve for up here. So we know that at time t equals 0, the derivative of I must have a value of 9.73, and that's in amps per second if you care about those sort of things. And all that I'm doing is summarizing here that the two initial conditions we have to satisfy are that the initial value of the current is 2.027 amps, and the initial value of the derivative of the current is 9.73 amps per second. So let's actually plug in those values and see what the unknowns that we're trying to solve for are, B1 and B2. When I plug in 0, e to the 0 will just become 1. Cos 0 will just become 1 as well, and sine 0 will become 0. So what that's going to leave me with is just B1. So even though this actual form of the solution looks more complicated than just a e to the s1t plus a2 e to the s2t, when you enforce the initial condition, it's actually really easy to solve for B1 directly. Now, how will we solve for B2? We'll enforce the initial condition on I prime of 0, and when you do that, I actually didn't write it up here, but hopefully everyone can see, you're going to have a 1 there, a 0 there, and a 1 there. So basically, from this first term, when you evaluate it at 0, you're just going to have B2 omega d. That's where that's coming from. When you evaluate this term at 0, you'll have a 1, but remember you got your minus alpha. The sine term is going to go away, but the cosine term will be 1. So we're going to have minus alpha B1 when that second portion of the function is evaluated at t equals 0. This has to be equal to whatever that initial condition is on I prime 0. We're trying to solve for B2, so just move the actual alpha B1 term to the other side and then divide by omega d. That's what we have here. be careful with your math, plug in, and you should get that B2 is 2.561 amps. Plug everything in, your value of alpha, your value of omega D, your B1 and your B2. And what we find is that that book, the solution rather, that the text told us would be true for I of T is in fact true. So even though these problems are cumbersome and they're long, and I remember when I took this class in person and I would watch my professor basically like that example, they would spend the whole class on, because you imagine someone writing it in real time, how long it would take. I'm probably thinking what I'm going to do for any kind of actual exam is to give you the second order problems as take-home problems. And then really what I want to see is not necessarily you solve some kind of innovative out-of-the-box problem, but just be able to replicate that process and show step by step how the initial conditions are determined, how the characteristic parameters of the circuit are determined, namely the alpha, the damping factor alpha, and the resonant frequency omega naught as a function of R, L, and C, and how you find your initial conditions and use them to determine the unknown constants in the general response.